Welcome all in this video lecture series. In this video lecture, we are going to solve the 0-1 knapsack problem, and we will try to exploit the use of a backtracking methods. Then we will generate a kind of a state space tree. If you want to know what do you mean by state space tree and how we can use a generalized approach in designing a state space tree, you can refer my other video that is specifically on the state space tree. And then we will see that from the solutions we will try to see that how this kind of link to the other techniques in the algorithm that also solve the same problem. So it's like there are two techniques that is solving a same problem. Then this video lecture series will be helpful to create the bridge between these two techniques and tell you that okay, from the one technique can you get it able to use the other technique to get it, because the backtracking will give you the solutions, and from those solutions you can use the other techniques. So let's first start with what do you mean by 0-1 knapsack problem. So consider this one instance of the 0-1 knapsack problem. What is this problem? In the 0-1 knapsack problem, we have given a one bag. That's we call the knapsack bag having a capacity. So consider in terms of kg that bag can hold only 12 kg. So if you go beyond the 12 kg, the bag will be teared down and all the items that you have put in the bag will be lost. And now what is the task? You are given certain items. Of course you cannot take all the items in a bag. If it is taken, fine, it is sold, but here you cannot take all the items, so you have to get the subset of items that you have to put in a bag. Now you have to put in a bag such a way that the profit or here value will be the maximum. So consider our real-time problem in the similar way. Let's say there is a one person who is doing a door-to-door marketing to sell certain items. Now that particular person is having a one bag. Within that, the person have to put all the items to carry on from door to door. Now what is the aim of the person? The aim of the person is to maximize the profit. So the person is having a certain items. Now person cannot take all the items in a bag. That's why the person thinks that if I take that subset of item that will give me a minimum profit, why I will go door to door and again after selling all the items I will get the minimum profit. So apart from that, the person will think on that better I will take all those items so that from without violating my bag capacity, without tear down my bag, even though I will going to sell all the items, the profit will be the maximum. So that's a real-time linkage of the 0-1 knapsack problem that we are right now we are using our day-to-day life. So when we are going out also we are taking a bags, and with the bags we will see that how the bag can handle. So that's what we will do. So here what we can do is here we have to find a subset of this set, because the total weight is 15. Here we can see if we take all the three items, and that's why our bag cannot handle a 15 kg. Now the second thing here is we cannot break the item. If we thought that okay fine, if we can't take particular amount of items entirely, we will break the item and we will take it. No, in the 0-1 knapsack, as the name suggests, 0 or 1. So either you can take the item or you can leave the item. So in this case you can know the answer, that is obviously item 1 and 2, that is 10 plus 2, that is 12 kg, and the total profit that you will get is 10 plus 5, that is a 15 kg. So what we have to do is now we have to generate a state space tree from this particular example, and then we have to go on. But before going to that, let's try to find out the linkages between the backtracking, why we are using the backtracking in this particular problem. So the question is, of course already we have a dynamic algorithms, that is we can use it to solve this 0-1 knapsack problem, but yet backtracking will kind of give you all the possible solutions. Only the problem with backtracking is that, well, the time, resources, space. If you have a multiple amount of time available, if you have resources available, you can use the backtracking. That's fine, you can go on. That is what the one advantage. Now the second advantage that we have explored, especially in this video lecture series, is that a pattern analysis. From the backtracking approach, we will generate a state space tree, we will generate the list of patterns. So like we will do in our research, when we do a research papers, when we do in research, what we do for a problem, so we will get a particular list of solutions. There are more solutions. Then what we do, we will try to find a patterns. If there is a pattern in the solution in terms of input, then that pattern we will try to relate in all other problems in the similar instance. So that will lead to a efficient algorithm. So from a non-efficient algorithm that will take much more time, we will lead to the efficient algorithm. So this video lecture is a bridge between these two. From a non-efficient, by analyzing that particular problems, we will give a solutions using the efficient algorithm techniques. That is what this will do, of course. So that's why once we get all the patterns, and the backtracking is the algorithm technique that will give us all the possible solutions of a given problem. That is their unique advantage, and that's why we will use the backtracking to get the answers. So yes, that is very intelligent, and yet the new method, that is we will use it. So we will exploit these things in our Statespace tree. So let's take our Statespace tree. So you can see this is the legend, profit, and the weight. Sorry. So the value and the weight. Now value is here, every items we have 10, 5, 6, weight is 10, 2 and 3. So we start with the initial solutions. That what we have done, we start with initial solution. Now why we start with initial solution in backtracking? Because we know that there is a solution possible for every problem. There is always a solution possible, and that's what we always start with, empty solutions, and then we will go. So when we start with a bag with a empty, we have a knapsack capacity bag of 12 kg. Till it's empty, there is no item that we have put. That's why the profit is 0 and current weight of the bag is 0. Now what we do, we will try to exploit the first item. First item we will use it. Now first item we will put item number 1. We don't require any kind of sorting here. That is 10 and 10. The 10 we got profit and the 10 is the weight. Now we are going to add the second items. So our bag is full, 12 kg, fine, profit 4. Now there is no need to further go because our bag is full. That's why there is no need to explore any other object in this particular path. So what we'll do, we will do the backtrack here. We will see, do is there any other item that is remains apart from 1 and 2? Yes, 3 remains, but can we take 3? No, because if we take item third, then the total weight become 13, and that's violate our bag conditions because our knapsack capacity is 12 kg. That's why this thing we cannot take. So again we will come to the particular root node from where we started. We will see we have explored this particular part. Now we have to explore the next item, that is 2. From the 2 again we will come to the 1. Yes, our bag is full. Now we don't have to explore any other further because our bag is full here. So that's our task here. This is also our task here. Here. Now again we will backtrack from here. Now again we will try to explore another. Yes, in the if we have a 2, we can also add 3. The moment we will add 3, our total weight will become 5. The profit will become 11. Now we cannot going to add the item 1 here, because if we add item 1 here, the weight will become 15, and that's why it is not allowed. Now you can see that compared to naive method, that is kind of intelligent naive method. That's if there is a feasibility maintained every time, then you are going to add the item. If there is no feasibility maintained, there is no need to explore that particular path ahead, because there is no meaning to go ahead, because if you don't get a solutions there. That's what the work intelligent naive method. So now again after this 3, we will again backtrack to the 2. Great. Now one thing you have observed here, that every time we will call and we will come back from the where we started. So that will kind of give us a tree approach. That's why this is a state space tree. Every state we have it, and we will take one actions. We will again go to the next stats. and that we continue. Again we start with here, we come here, then it will call here the third one. Well, we will pick the item third because it will maintain our feasibility. Now we will come to the item 2. It will be 11 and 5. Yes, but we cannot further because if we take item 1 our capacity become 15. Not possible to continue. So use the intelligent approach. Again come back. Can we take item 1? No, this we cannot take it. So again come back from where we started. Okay, so now with you can say the maximum profit that we got here is the 15 and the weight is 12. So our solution vector will be 1 and 2. Okay, so of course from the given techniques like greedy, divide, dynamic programming, divide and conquer, we can see divide and conquer. Well, it doesn't looks like because we have to divide the problem, that doesn't looks to me. Now the greedy, because I1, I2 first and second item is selected. Well, there is no any kind of a relations between 1 and 2 that will, because in the greedy you have to find a greedy criteria, and according to criteria you have to continue. So that's not I am missing here. So the only technique that is remains is dynamic programming. So that's why there is a chance that if the technique that is possible here, that is a dynamic programming to solve this particular 0-1 knapsack problem in an efficient way. So now only we have to resort to the dynamic programming and we can use that particular optimal substructure property to get our answer. That is what the things here. So I hope that using this particular Statespace tree of a backtracking, you are kind of getting a bridge between the two particular technique of a backtracking and dynamic programming, and that will try to help you to narrow down your list of techniques to be possible, and within that technique you can try to do something better and better. So this will be the references that you can try to use to understand in detail of the 0-1 knapsack problem, as well as in backtracking. You can look at the NPTEL videos, the MIT open lectures, as well as any other relevant material in terms of a knapsack problem. Even there are approximations algorithm available that you can try to study, that if you don't get exact answer, you will try to get an answer that is a near optimal to that particular answers. And you can use the internet to go to in detail of the knapsacks, the dynamic programming version of the knapsack that you can try to visit. So I hope that using this video that you will try to get motivated to apply a backtracking approach in the other problems. Try to generate a state space tree, and from the tree that you will try to analyze the patterns in the solutions, and from that solutions pattern you will try to find out a technique that is possible to apply and try to get your answers. Thank you for watching this video.